Okay, good morning, everyone. Welcome back to a new week. Though pangatlong, ano na ba ngayon? Wednesday na nga ba ngayon? Hindi. Tama, Wednesday na pala ngayon, no? Middle week na uli. So, I hope you guys had a good laboratory class last Monday. Though wala tayong new discussion, but I hope you took advantage of your lab instructors. You ask for their help if you have some questions about the laboratory excerpt. So may problema kayo about programming or you're still adjusting and you say shifted to MATLAB or used Python as what your lab instructors might have been using. So please join them during the lab classes kahit wala tayong mga discussions para you can ask them questions. And that's the reason why lab excerpts are due late on Mondays para you can still consult with your lab instructors during Mondays about the lab exer and any technical difficulties that you might have encountered, right? So remember, bulk of your grade comes from the lab exer, so might as well ask for help, right? So tanong kayo sa lab instructors, tanong din kayo sa akin, pwede rin. So basta make sure that you submit your laboratory exercises and try to do your best on them. Okay. Now, going back, we're still in module 4, and I hope to finish it this week. Really, the laboratory exercise associated with this module is due on Monday, October 18. And then upload ko na rin yung module 5, though the exercise supposedly siya dapat yung sa coming Monday pero minove ko na siya ng 1 week para hindi tayo magmadali with the lecture kasi we have 2 weeks buffer naman sa 174 so we can take our time. So today we'll continue our discussion about piecewise linear interpolants and sabi natin last time, okay, parang almost perfect na yung na-develop nating interpolation theory. Again, interpolation is a type of approximation wherein we want our approximating function to pass through the points given in the data. So kung meron tayong 11 data points, gusto natin makabuo ng interpolating function na dadaan dun sa 10 o dun sa 11 data points na yon. And that's the distinguishing property of interpolation against other form of approximations, right? And then we developed the theory. Sabi natin meron lang isang unique algebraic interpolating polynomial of degree at most n for a given n plus 1 data points, right? And then nakita natin yung error term para sa kanya. Yung error term para sa kanya ay comprised of the n plus 1 derivative evaluated at some number over n plus 1 factorial times some factor omega, which is the product of x minus exabytes, where the exabytes are your interpolatory abscissas. And then tinignan natin, paano natin mapapababa itong error term na to? And we learned from last week na meron dalawang paraan. If you want to minimize omega with respect to L infinity norm, then piliin mo yung exabytes to be the roots of the Chebyshev polynomial of the appropriate degree. Now, if you want to minimize omega with respect to the L2 norm, then you should choose the exabytes to be the roots of the Legendre polynomial or the Legendre polynomial of, again, the appropriate order. Tapos, mukhang perfect na. So, kasi napapababa natin yung error, napapaganda natin siya by an appropriate choice of the exabytes. However, we discovered during our last lecture that there might be some problems whenever we are dealing with high degree polynomials. And that is common whenever we have lots of data points. We call that the Runge phenomenon, wherein oscillations or crazy wiggles occur near the boundary of the interpolatory interval whenever the interpolating polynomial is a polynomial of a high degree. Okay? So, and then nangyayari siya kahit sa mga nice enough functions, so sa mga smooth functions. So, kailangan nating bantayan ang ating interpolation method, lalo na kapag napakalaki na ng polynomial because it might be subject to the Runge phenomenon where the L infinity norm of the error blows up due to the oscillations near the end or near the boundaries of our interpolatory interval. And our remedy there is Kung hindi pala maganda na gumamit ng polynomial na malaki yung degree, edi gumamit tayo ng mabababang degree na polynomial. And let's do this by subdividing the interpolatory interval into several subintervals, depending on the number of data points that you have. And between these two consecutive data points, let's use a lower degree polynomial that will interpolate the function on those two endpoints. So nangyari, we are pasting together. Nagdidikit-dikit tayo ng mga polynomial na mabababa yung degree para makabuo ng isang function na nagmimimic doon sa given data natin. Now, here, it is not a polynomial interpolation anymore because we have a piecewise function na. Conditional na yung function na nabubuo natin. And the easiest one that we have seen last time are the piecewise linear interpolants, wherein we are building up a function S that, number one, interpolates the given data points, and number two, it is each piece of the conditional function S is linear on each subinterval, and third, it is continuous. And again, the only possible points of this continuity would be at the boundary points. Yung mga napili nating yung mga given o napili natin na exabytes. So having said that, with these three conditions, we're able to characterize the piecewise polynomial. By considering the A subice to be the data points and the B subice to be the slopes of the line passing through two consecutive data points. Yun yung dinerive natin last time. And we had an example 4.1 wherein we used piecewise linear interpolants in order to approximate the probability that an exam score in Math 174 way back 2013-2014 is passing. So yan yung huli nating nakita from last week. Now, we'll continue with example 4.2, but that example talks about the error bound. Okay, and for that we'll use theorem 1, which we presented without proof. Don't worry, I won't ask you to prove this. Let's just accept this as a fact. So if the function f is or if the function f has continuous second derivative, so yun yung ibig sabihin ng C upper 2 of AB. Si f ay continuous as well as its first and second derivatives, and S be the piecewise linear interpolant of f relative to a partition of the domain into your interpolatory abscissas x1 until x sub n plus 1, then the L infinity norm of the error, or in other words, the maximum of the absolute difference between f of x and s of x over the interval AB is no more than 1/8 h squared maximum value ng second derivative of f evaluated over the interval AB, where h is the maximum length of a subinterval. Okay? So ito yung error bound. 1/8 times yung pinakamahabang length ng isang interval or pinakamalaking length ng isang interval times the maximum value of the second derivative. And you will see here, bakit kailangan yung si f ay mag-belong sa C upper 2? Bakit dapat continuous hanggang second derivative ni f on the closed interval AB? It is needed because we are maximizing f double prime, or this is a good assumption because this guarantees that f double prime will have, being continuous, will have a maximum value over the interval AB, and that will occur over an x value over that interval. So nag-exist itong maximum ng second derivative dahil siya ay continuous via the extreme value theorem. Okay. And then, yeah, this will constitute the bound or the error bound for the approximation or the interpolation using piecewise linear interpolants. And you see that it doesn't so much depend on the number of points used nor the choice of the exabytes. Kakaroon lang ng effect yung number of points at saka yung mga exabytes na ginamit sa pagko-compute ni H. Pero si H naman ay maximum na haba, pinakamahabang length ng pinakamahabang interval. So ibig sabihin, the idea here is if you increase the value of n, pag pinalaki mo ng pinalaki yung n, mas malaki yung chance na maliit yung h kasi marami ka ng subdivision points na ginagamit. And note that in our definition of the piecewise linear interpolants, hindi necessary na equally spaced. Hindi kailangan pare-parehas yung x sub I plus 1 minus x sub I. So posibleng may mas mahabang intervals. If you get the maximum of that, siya yung value ni h. Alright? So pwedeng piliin mo siya equally spaced, pwede namang kalat-kalat depending on how crazy your function behaves. Kasi may mga function na maganda yung behavior, say, from sa kalahati ng interval, tapos napaka-oscillatory niya na dun sa other half ng interval. So, minsan gusto mong mag-adaptive mesh, mas marami kang points na gamitin dun sa medyo messy yung behavior ng function natin, right? So that's why we don't usually impose uniform lengths of the intervals, especially if our function doesn't behave crazily, okay? But this is the error bound. So let's see a specific example. Medyo sinauning example. Kasi ngayon meron na tayong mga calculators which can approximate sines and cosines. Pero in here, a textbook editor or a textbook publisher needs a table of values for the sine and cosine functions. And each function is to be tabulated at equal increments from 0 degrees to 45 degrees. The values in the table will be given to 6 decimal places, and the increment in theta must be small enough so that the linear interpolation between consecutive values will introduce an error less than 10 to the minus 6. What are the allowable values of the increment? Again, dun sa error bound, mukhang nakadepende lang yung error bound or yung error estimate natin sa length ng bawat subinterval. So itong textbook publisher na to, gusto niyang mag-display ng table of values ng sines and cosines from 0 to 45 degrees using 6 decimal places. That's why it makes sense kung bakit ang error gusto niya mas mababa sa 10 to the minus 6 para covered niya lahat ng decimal digits. Okay? Now, ano daw dapat? So kung equally spaced yung pipiliin niyang points from 0 degrees to 45 degrees, ano dapat daw si h para yung error hindi lalampas ng 10 to the minus 6? Excuse me, guys. Okay. Now, we'll make use of the error bound. So, gusto natin yung error hindi lumampas sa 10 to the minus 6. Eh, ang alam natin ay maximum possible error. So, pag sinet natin yung maximum possible error to not go beyond 10 to the minus 6, then we would have satisfied yung kailangan ng textbook publisher. So, titingnan natin yung error bound. Medyo weird ba yung example na nagpapatabulate yung yung textbook publisher ng sine and cosine functions? In the prior to the invention of calculators, medyo ganito yung trabaho ng mga mathematicians. May mga mathematicians ang trabaho nila mag-compile ng table of values para sa transcendental functions like sines, cosine, logarithms, tapos yun yung binibenta nila. And nung high school kami, ganito rin yung ginagawa namin. May table of values sa dulo ng trig books namin. Pero hindi naman ganun katagalan after yung pagiging high school ko. Pero naabutan pa namin nung high school to. Pero I doubt na naabutan nyo pa yung paggamit ng table of values sa likod ng mga books. But anyway, kasi mura na yung mga calculators ng time nyo, no? But anyway, so yeah, this is the error bound. And then we calculate f double prime. So ang function to be approximated natin ay sines and cosines. And it doesn't matter if it's a sine or a cosine function. When we take the second derivative, it will just be negative sine or negative cosine. Tama ba? Yun yung second derivative niya. But nevertheless, if it's positive or negative sine or positive or negative cosine, papasok naman siya dun sa absolute value. So, mawawala na siya. So, eventually, f double prime or its absolute value is either sine or cosine. We get its maximum from 0 to pi over 4, but we don't really need to be very meticulous about it. Kasi si sine and cosine, whatever the angle is, we know that this will always be less than 1. Right? So that's why I assume without any further calculation in f double prime, alam ko sine and cosine lang naman siya. It doesn't matter over what interval, lagi siyang less than 1. So that's what I'll use here. I'll use 1 to be the replacement for the maximum of f double prime. Okay. Actually, dapat pala inequality to. So take note of that. Kasi yung maximum value ni f double prime ay laging mas maliit sa 1. So if I replace this by 1, mas bababa yung, or sorry, mas malaki yung makukuha kong value. Alright? So now, the error term or the error estimate is now reduced to h squared over 8. And again, we want the error not to exceed 10 to the minus 6. Alam ko ang pinakamalaking posibleng error ay hindi tataas ng 1/8 h squared. So I will set 1/8 h squared to be less than 10 to the minus 6. And in doing so, yung actual error ay nandito, tama? At yung actual error nandito sa dulo ng inequality. So with this imposition, we guarantee that the actual error will not go beyond 10 to the minus 6. All right? And then all we need to do is to play with this inequality and solve for h. Multiply both sides by 8, you get this guy. Take the square root of both sides, so we get this bound, and that would be approximately 0.00282843. So that tells us that the increment should be no more than 0.00282843 radians, so be careful. We're working with real numbers here, so yung degree of measure ay laging radians. So if you want to talk about degrees, kasi yung problem given in terms of degrees, convert natin to into degrees. So hopefully tama yung pagkaka-convert ko, you get around 0.16 degrees. So if the textbook editor wants to have relative error, would like absolute error less than 10 to the minus 6, then the increment must be no more than 0.1620. Okay? So yun yung idea dito. Though mapapansin nyo, siguro medyo pessimistic itong error bound na nakuha natin. Kasi, let's see. Kapag ka si f ay sin x, so yung second derivative niya ay what? Sine, cosine, negative sine. Okay. Tapos pag kinuha natin yung absolute value, mawawala lang naman yung sine niya. Pero over the interval 0 to pi over 4, si sine ay, anong maximum value ni sine? Ang maximum value lang ni sine ay square root of 2 over 2. Pero ang pinampalit natin dito ay 1. So that means medyo pessimistic pa itong bound na to. Medyo conservative, o medyo careful pa yung bound na to. So hindi ko ginamit yung pinaka-tight na bound na alam ko para dun sa f double prime. Kasi pinagsabay ko yung computation ng sine and cosine. Yung cosine, ang second derivative niya ay what? Negative cosine. Pero ang maximum talaga ng cosine from 0 to pi over 4 ay equal kay 1. So ito na talaga yung pinakamagandang error, pinakamagandang h na pwede nating i-impose kay cosine. Pero kay sine, pwede pa nating pababain o palakihin yung value ni h. Kasi the bigger the value of h is, the larger possibly the error becomes. Right? So pero pessimistic nga itong estimate para kay sine. Okay na to kay cosine pero pessimistic pa siya kay sine. So tingnan natin kung ano yung kaya nating i-afford para kay sine. Kasi ano yung drawback na malaki yung maliit yung value ni h. Sige nga. Ano yung drawback kapag ka si h ay maliit? Of course, ang advantage niya pag maliit si h, maliit yung error, right? Pero ano yung drawback niya? Sige nga. Anyone? Kasi ang gusto nung textbook publisher, yung error hindi lumampas ng 10 to the minus 6. And sir, gawin ko yung error ay 10 to the minus 10. And I think that would be small enough so that the error is not more than 10 to the minus 6. Pero ano yung disadvantage na napakaliit ng value ni h? Kaya gusto kong tingnan gaano ko kataas pwedeng i-push si h para yung error ay hindi pero na-maintain na yung error ay hindi lumalampas ng 10 to the minus 6. Walang gustong humula? Sayang naman yung mga bonus sa prob sets. Okay. So, but basically the disadvantages sa numerical analysis, laging give and take yan eh. So if you want lower errors, pag gusto mong mababa yung errors, you have to pay something. Okay? So meron yan laging kapalit. Para yung Full Metal Alchemy. You have to give up something of equal or greater value to achieve something. Hindi ka nakapag-transmute out of nothing. Nice try, Noriel. Magiging high degree yung polynomial. Hindi na natin siya problema sa piecewise interpolants. Kasi sa piecewise interpolants, kahit maraming points tayong ginagamit, nagko-connect the dots lang naman tayo, or we connect two consecutive exabytes by a straight line. So laging linear pa rin yung degree ng bawat piraso nung ating conditional function. So yeah. Pero the idea here is the smaller h is, the lower the error, of course, but the more exabytes you are using. Tama? Kasi lumiliit yung increment, so dumarami yung points na ginagamit mo. And the more points that you use, the more computations you need to do. Because kung meron kang n plus 1 points, kailangan mo magkakaroon tayo ng n na piraso ng conditional function. And that will entail lots of calculations kasi sa bawat n or sa bawat isa ng n na functions na yon, nagko-compute tayo ng dalawang parameters, a sabay at saka si b sabay. So the smaller h becomes, the more points we are using, the more work should be done insofar as computing those parameters are. So lumalaki yung computational expense natin. So kaya hindi mo gusto na magbigay lang ng obviously napakaliit na h. Kasi pag sobrang liit niya, which is smaller than what you needed, you will satisfy your error bound, pero mas marami kang trabaho na kailangan gawin. Okay? Kaya hinahanap natin ano yung pinakamagandang value ni h. Na hindi siya ganun kaliit, pero hindi siya malaki, so that nasa-satisfy natin yung gusto nating error. So, kung gusto ko pa lalong magtipid, sige, mag-compute ako ng isang tighter bound para dun sa error sa sign. Ito na yung gagamitin ko sa cosine kasi wala naman tayong choice na. Pero para sa kaso ng sine, yung h squared over 8, maximum of the second derivative over the interval 0 to pi over 4 ay equals sa h squared over 8 times square root of 2 over 2. Kasi si square root of 2 over 2, siya yung maximum value ng sine sa interval 0 to pi over 4. Tama? Kasi increasing si sine sa interval na to, so it will attain the maximum value dun sa pinakamataas na value ni theta, o pinakamalaking value ni x. At yun na yung pi over 4. Sine of pi over 4 is root 2 over 2. And so this is, okay, and we want this to be less than 10 to the minus 6. Okay. Gusto natin yung pinakamalaking error, mas maliit sa 10 to the minus 6. So, that being said, solve ko lang tong inequality na to. So, this is, we'll have h squared is less than or equal to 16 over root 2, 10 to the minus 6. And then you can compute for h here. After taking the square root of both sides, I think you'll get something like 0.03. Nakalimutan ko na. Tingnan ko sa kabilang section. Ginawa ko to sa kabilang section eh. Oops. 3363. Okay, 3363. 0.03003363. Okay? So ito yung nakuha kong value ni h once I compute this. So ibig sabihin, kay sine pala, paggagawa ko ng sine table, pwedeng yung increment can go as high as 0.003363. Tapos yung error ay less than or equal pa rin sa 10 to the minus 6. So I say this is a tighter bound compared to this one kasi pwede ko rin itong gamitin sa sign. Right? Kasi pagka yung h ay anything smaller than 0.003363, guaranteed na satisfy yung error bound. So pwede ko pa rin itong gamitin kasi mas maliit to dun sa h yung na-compute ko para kay sign. So kung medyo OC yung textbook publisher, gusto niya parehas na lang yung theta values na gagamitin niya, gagamitin niya yung mas maliit na h value para kay sine and cosine. Kasi pagka lumiit dito, or pag mas malaki dito yung ginamit niyang increment, hindi na siya sure kung yung error dun sa cosine approximations ay hindi lalampas ng 10 to the minus 6. Okay? Does this make sense? Okay lang ba? So ito yung isang idea dun sa paggamit ng error bound. Okay, so you can manipulate it in order to satisfy whatever error requirement or error threshold you have in mind. So these are the smallest values of h, or sorry, these are the largest value of h that you can use so that the error will not go beyond 10 to the minus 6. But again, if you choose anything smaller than these h values, then medyo conservative yung choice mo. Mas mababa yung error na makukuha mo, pero mas marami kang work na kailangan gawin. Kasi that will entail more points para magamit. Okay, any questions? So I guess that ends the discussion about piecewise linear interpolation. Any questions? Wala naman? Or masyado pang maaga para sa questions? Okay. So I hope you're still there, enjoying your coffee or your breakfast. So, okay. Let's continue and hopefully go at least further into this module. Now, mukhang okay na itong theory na na-develop natin so far. Problema pala yung wiggles, di gumamit ako ng low degree polynomials. I'll just paste together linear functions. Kaya lang merong isang problema sa pagpipaste ng mga linear functions. So remember, this is our illustration of a piecewise linear interpolant to the Runge function. Now, continuous to, pero ang problema, hindi siya smooth. Merong mga sharp turns, especially possibly at the boundary points. So nangyayari ay continuous nga siya pero hindi naman siya differentiable dun sa mga boundary points. Kasi dun sa mga boundary points, since we are pasting together linear functions, dito sa boundary points, pwedeng napaka-sharp ng turn, like this one. And kahit nga dito, sharp na rin yung turn. Mula dito, tapos bigla siyang magaganito. So hindi talaga siya differentiable dun sa boundary points. And differentiability often is a very important condition for functions. All right. So remember sa calculus, maraming mga bagay or maraming mga applications na kailangan differentiable yung function mo. So if we want our model to be of value theoretically, or insofar as the tools of analysis are concerned, then gusto natin ay maging differentiable yung function na kinoconsider natin. Kaya lang ang problema, wala na tayong degree of freedom dito sa piecewise linear interpolants. Kasi however we define the piecewise linear interpolants, dahil linear yung mga magkakasunod na piece, ibig sabihin hindi talaga natin ma-avoid yung possible discontinuity or possible non-differentiability at the boundary points. So that will prompt us to use higher degree interpolants. So hindi naman sinabi na kailangan nating mag-stick sa linear. So why not let's try pasting together quadratic functions. Instead na linear functions, sige, try natin quadratic. So parabola dito, may parabola ka kunwari dyan, part ng parabola dito, tapos part uli ng parabola doon, then pag ganito, and so on. So on each piece, I can define the function to be a quadratic function. And if I do so, I will have enough degrees of freedom to not just ask for continuity of the pieces at the boundary points, but I can also impose differentiability at the boundary points. Kasi magkakaroon tayo ng additional degrees of freedom doon. Kasi ang itsura na nung S sub i's natin doon ay ganito. A sub I plus B times X minus X sub I plus C sub I X minus X sub I squared. So ngayon, may additional degree of freedom na tayo. May isang parameter tayong nadagdag pag quadratic function yung gagamitin natin. May mga C sub i's na tayo. And this C sub i's can be chosen nicely so that differentiability is ensured at the boundary points. Tapos hopefully makikita nyo naman yung idea na pag kaya natin mag-define ng part ng parabola so that yung consecutive points ay smoothly connected to each other. Okay? Now, this is the second step, and this is an example of a spline. Yung mga splines, sila ay mga differentiable na conditional functions that interpolates a given function. So, para matawag na spline, dapat siya ay differentiable. So, of course, piecewise linear interpolants, by this definition, are not splines because they are not necessarily differentiable at the boundary points. Pero we can define parabolic splines or quadratic splines because the parameters of the quadratic pieces can be chosen to ensure differentiability at the boundary points. Okay? Kaya lang, hindi ko na sinama yung splines sa discussion. So, pwede nyong i-consult yung mga numerical analysis books or websites if you're interested into looking at parabolic splines. Pwede nyo siyang gamitin sa project if you want. So, you can take a note of this. Paano nagde-derive ng cubic splines? Quadratic splines. But you will have sort of an idea how it is done because we will look into details on how to derive the cubic splines. Makita nyo later. Okay? Pwede nyo siyang i-apply. Mas madali pa nga yung derivation ng quadratic splines kesa dun sa gagawin natin for cubic splines. Okay? So you can use that in your project, quadratic splines, if you want. Isa pang pwede nyo tingnan ay Bezier curves, which I think are examples of splines as well. So pwede nyo siyang tingnan. Pero trigonometric yata yung gamit na pieces doon. So yeah. Or parametric function ang ginagamit doon. So you can take a look at those topics that we didn't cover, okay? But let's go to section C. So here, sinulat ko naman yung definition ng splines. They are smooth, piecewise interpolants. And formally, we have in definition to ano nga ba yung isang cubic spline? Well, a cubic spline interpolant of F relative to a given partitioning of the interpolatory interval AB into abscissas x1, x2, xn until x sub n plus 1. It is a function S, a conditional function S that satisfies the following conditions. Number 1, sa bawat subinterval, dapat yung piraso ni S ay isang cubic polynomial S sub I. So remember, meron tayong n plus 1 points. So ibig sabihin, meron tayong n na piraso na kailangang i-define kasi meron tayong n subintervals na lalabas. Kung meron tayong n subintervals, sa bawat subinterval, gusto ko cubic yung polynomial para dun sa interval na yon. At yung piraso na yon ni S, tatawagin nating S sub I. Okay? Second condition, interpolatory condition. Ibig sabihin yung function value ng isang abscissa under the interpolant should be equal to the given function value. Kasi dapat dadaan pa rin tayo dun sa given data points kasi interpolation pa rin naman itong piecewise itong cubic splines. Okay? So that's why we have the interpolatory requirement. And conditions 3, 4, and 5 are added bonuses. Ito yung mga additional properties na gusto nating masatisfy ni S. Of course, it makes sense that we want continuity to be guaranteed. Second, S prime must also be continuous. So we're imposing smoothness to our function. Kasi gusto natin hindi lang nag-exist si S prime, pero gusto natin si S prime continuous na rin. And we also want, as an added safeguard, si S double prime maging continuous din. And you will see later that we can afford to impose all these 5 conditions kasi marami tayong degrees of freedom. Okay? So specifically to derive how the formula for the for the cubic splines, gagamitin natin bawat isang condition na to. Titingnan natin kung ano yung ini-imply na condition, ini-imply na mathematical condition ng bawat isa dun sa limang parts ng definition. Okay? Now remember in part 1, we want each piece S sub I to become a cubic polynomial. So here, I translated that mathematically and I said, siguro yung mga S sub i's dapat ang itsura nila ay given by this equation. Okay? So and by inspection, these are really cubic polynomials, and we do this for I going from 1 to n. Kasi meron tayong n pieces. Kailangan ko ng S1 hanggang Sn. At bawat isang S sub I dapat cubic. Ipagpapalagay ko ng itsura nila ay ganito. Okay? So that means we are looking for 4 parameters for each of the S sub i's. Kailangan natin computein ano yung AI, BI, CI, at DI para ma-completely determine natin si S sub I. Pero ilang S sub I meron tayo? I goes from 1 to n. So we have a total of n unknown functions. Each function has 4 unknown parameters. So in all, we are looking for 4n parameters. Ito nga yung cost. If you want to have better approximation, you have to do more work. So kanina sa piecewise linear interpolant, ang kailangan lang natin ay 2 parameters para sa bawat piraso ng function. Okay? Dito 4 sa bawat function. So mas maraming parameters tayong kailangan computein. Okay? And how do we compute these parameters? AI, BI, CI, and DI. Gagamitin natin yung 4 na natitirang conditions dun sa definition. The second condition is the interpolatory requirement, and that is translated in equation 4.3. Dapat yung S sub I of X sub I, because remember, si S sub I, siya yung function, siya yung piece ng conditional function para sa interval X sub I until X sub I plus 1. Valid si S sub I dun sa interval na to. So in order to satisfy the interpolatory requirement, I want that when I plug in X sub I inside of Si, dapat ang makukuha ko ay yung given function value. Alright? Pero kapag pinlogin ko si X sub I dun sa ansatz o dun sa template ko para sa S sub I, remember ito yung S sub I, pag pinlogin ko si X sub I for all x's here, sige, plug in natin. Ano mangyayari? This vanishes, this vanishes as well. So, kaya ganito yung gusto kong itsura ni S sub I para madaling mag-substitute. Alright? Pag nag-substitute ako ng X sub I, magzi-zero lahat ng may X. Alright? So that means S sub I of X sub I should really be just equal to A sub I. And this should be true until f of X sub I. This should be true for all I from 1 to n plus 1. So ibig sabihin dito sa equation 4.3, we will have how many equations? We will have n plus 1 equations. Okay? So ito yung dapat nating i-guarantee. Meron tayong n plus 1 conditions coming off of equation 4.3. Medyo may caveat pala dito ng konti. Ito ay totoo hanggang kay n lang. Kasi remember hanggang s sub n lang tayo. Pero may isang additional condition, kailangan interpolatory pa rin dun sa dulong endpoint. So ibig sabihin yung S sub n of X sub n plus 1 ay equal kay A sub n, which is f of X sub n. Kasi remember, dapat dapat dumaan din siya dun sa huling data point, which is the data point corresponding to the abscissa X sub n plus 1. Pero wala na tayong S sub n plus 1. Remember, hanggang S sub n lang yung meron tayo. So, ibig sabihin, yung huling sub-interval, ang nag-govern sa kanya, si S sub n. So, dapat pag pinlogin ko si X sub n plus 1, yung huli nating abscissa, dun sa pinakahuling piraso ng spline, dapat equal siya dun sa function value. Okay? So, that's how we get the total of n plus 1 conditions coming from the interpolatory requirement. And then punta tayo dun sa pangalawang condition, continuous. Remember kung ito si x sub I, ito si x sub I plus 1, ito si x sub I plus 2. Right? Dito sa piece na to may cubic function. Tawagin natin siyang SI. May cubic function dito, say S sub I plus 1. We want continuity. So ibig sabihin, yung function value ni S sub I at saka ni S sub I plus 1 dapat equal sa x equals x sub I plus 1. Right? Para mag-join, para magdikit yung dalawang cubic functions na gusto nating mag-govern sa bawat subintervals. So that's why I want to impose that S sub I of x sub I plus 1 is equal to S sub I plus 1 of x sub I plus 1. Para parehas sila ng function value dun sa dugsungan nilang dalawa. Okay? Is that clear kung bakit ito yung translation ng continuity requirement? Okay? Now, tignan natin ano yung ibibigay sa atin ng equation na yon. Well, unahin natin itong S sub I plus 1. Ipa-plug in ko siya dun sa, unahin muna natin pala to. S sub I of X sub I plus 1. Ipa-plug in ko si X sub I plus 1 kay SI. So, ito ay I plus 1. Ito ay magiging I plus 1. Ito ay magiging I plus 1. Okay? And then I'll introduce a notation. Let's call X sub I plus 1 minus X sub I as H sub I. Okay, tawagin natin siyang H sub I because that is really the step size, the length of the ith subinterval. So siya yung difference between X sub I plus 1 and HI. So in essence, that means S sub I of X sub I plus 1 will be equal to A sub I, B sub I, H sub I squared. Wala palang square. Oops. Plus CI X H sub I squared plus DI H sub I cubed. And that's what we have here. All right. And then, kapag naman ipa-plug in ko si X sub I plus 1 kay S sub I plus 1, look at the first condition. Lagi lang siyang nagiging A sub I. Pag parehas yung index nung piece at saka nung abscissa na pina-plug in natin, equal lang daw siya kay A sub I or A sub the common subscript. So since in this guy, the function and the abscissa has this or have the same subscript, so ibig sabihin equal lang siya sa A sub I plus 1. Alright? Or kung ayaw nyong maniwala, palitan nyo lahat ng I dito ng I plus 1, tapos i-plug in nyo si X sub I plus 1, you will get A sub I plus 1. And let's call this equation 4.4. Siya yung nanggaling sa continuity requirement. Okay? Now, we still have two continuity requirements left and they are for the derivatives. So, tingnan natin to. Compute natin yung first derivative. Kasi gusto natin continuous yung first derivative. So, that means S prime or S sub I plus 1 prime must be equal, or the function value of S sub I plus 1 prime at X sub I plus 1 must be equal to the derivative of SI at the point X sub I plus 1. Kasi dapat equal yung derivatives dun sa boundary points. Kasi gusto natin continuous yung derivatives. Alright? So dahil continuous yung derivatives, dapat totoo tong equality na to. So compute natin yung S sub I prime. Si S sub I prime ay equal lamang sa B sub I plus 2CI X minus X sub I plus 3di X minus X sub I. Nag-differentiate ako with respect to X. May square pa tong matitira. Okay? So ito yung first derivative. Now, if we plug in X sub I plus 1 here, we will get bi ay nandun pa rin. Tapos ito ay magiging 2CI HI. And then this would be 3di HI squared. Kasi yung X sub I plus 1 minus X sub I ay napapalitan natin ng H sub I. Right? And However, for this guy, S sub I plus 1 prime evaluated at X sub I plus 1 will just be B sub I plus 1. Kasi pag pinalitan natin dito lahat ng i's by plus 1, tapos nag-plug in tayo ng X sub I plus 1, itong may mga x's, nagzi-zero sila. Natitira lang yung B sub I plus 1, kaya siya pupunta ron. Okay? Now, let's call this equation 4.5. Yung nanggaling sa continuity ng derivatives. Okay. May isa pa, kasi dapat continuous yung S double prime. So we'll do the similar thing, but this time for S double prime. Computin yung second derivative na to. And true enough, if you plug in X sub I plus 1 to both S sub I plus 1 double prime and S sub I double prime, you will get this equation. We'll call it 4.6. Okay? Masyadong maraming equations, no? Let me borrow 5 more minutes or so para matapos ko lang yung derivation nito. Pero mukhang di pa rin natin matatapos yung module 4 today. But that's fine. Okay? I'll just walk you through the different steps. Pero nagawa na naman natin yung pinaka-komplikadong part. Now, ito ay careful manipulation pero medyo messy or cumbersome yung mangyayaring manipulation. So, look at equation 4.6. From equation 4.6, I will compute for D sub I in terms of the other remaining variables. Remember, ang goal natin mahanap si AI, BI, CI, at DI. Kasi pag nahanap din natin sila, mako-compute na natin yung yung cubic spline. Right? Kailangan ko siyang i-compute. Oh, by the way, how many equations do we have so far? Now, here we have we'll have n minus 1 equations here. Here we'll have n minus 1 equations as well. Dito ay n minus 1 din. Kasi they will be valid from 1 until n minus 1. Okay? Kasi wala namang piece that will join together yung dalawang boundary points. So meron tayong total of n plus 1 points. Wala tayong continuity requirement na ini-impose kay x1 at saka kay x sub n plus 1 kasi wala naman ng functions na kadugsong yung mga piraso that governs their intervals. So meron tayong n plus 1 minus 2 continuity requirements na kayang i-impose. So kaya meron tayong n minus 1 equations whenever continuity is involved. So kaya may n minus 1, ilan yung total? So this gives us a total of 4n minus 2 equations. Okay. So kaya lang, ilan yung hinahanap natin? We're looking for 4n parameters. 4n yung parameters na hindi natin alam. Pero meron lang tayong 4n minus 2 equations. Mas marami yung variables or mas marami yung unknowns kesa dun sa number of equations. So that means there will be multiple solutions to this problem. So there might be more than one set of parameters that will satisfy all 5 conditions. And that gave rise to different types of cubic splines. Okay? Pero siguro ngayon, tingnan muna natin ano yung generic derivation. Ano yung makukuha natin out of the 4n minus 2 equations. Pero tandaan natin, meron tayong dalawang free conditions na pwedeng i-impose later depending on what type of cubic spline we want to build. Okay? So pero i-derive muna natin yung generic. Hanapin yung equations, yung 4n minus 2 equations that are implied or are required by the definition. Okay. So again, si 4.7 nanggaling sa 4.6 by solving for the D sub i's. And you see here that the D sub i's are expressed in terms of the C sub i's. And then using 4.7 in 4.4, ito si 4.4. So yung DI dito kay 4.4, papalitan ko lang galing kay 4.7. I will get this. Okay. Or, actually, alam na pala natin yung A sub i's, no? Kasi yung A sub I, sila lang yung function values. A sub I is equal to f of x sub i's courtesy of the interpolatory requirement. So tapos na yung A sub i's. Alam na pala natin siya. So tatlong sets na lang ng parameters ang hinahanap natin. In 4.7, we have written D sub I in terms of the C sub i's. And then in using 4.7, in 4.4, pwede kong masulat ito. But again, we already know the A sub i's. So from here, I will compute for the B sub i's. And I'll get equation 4.8. Kinompute niya lang si B sub i's. The beauty of equation 4.8, nagdidepend lang siya sa A sub i's that we know to be the function values given in the problem. And then yung mga C sub i's, hindi pa rin natin alam. Okay? Pero remember, si D ay nasulat natin in terms of the C sub i's. Now, si B sub i's, na-compute na rin nasulat na rin natin in terms of the C sub i's. So the problem now is reduced to finding the C sub i's. Because once we know the C sub i's, mako-compute na natin yung B sub i's, mako-compute na rin natin yung D sub i's, and then we're done. Okay? Now, pero paano natin mahanap yung C sub i's? Well, I will use equation 4.7 again in equation 4.5. Paltan ko uli yung mga di's kay 4.5 by 4.7, I will get 4.9. Okay. Ito yung makukuha ko pag ginawa ko yon. Okay. And then what I'll do now is I'm going to use equation 4.8 into 4.9. So yung BI dito, papalitan ko neto. Okay, pa-plugin ko siya dyan. Tapos kukunin ko yung corresponding version ng 4.8 para kay I plus 1. So lahat lang ng subscript madadagdagan ng isa. Ito ay plus 1, ito ay plus 2, ito ay H sub I plus 1. Okay. So itong expression na to para kay B sub I plus 1, ipapalit ko rin dito. Okay. And if we will re-index yung I plus 1 gagawin ko, I plus 2 gagawin kong I plus 1, yung I plus 1 gagawin kong I, yung I gagawin kong I minus 1, I will get this equation. Okay? Nag-re-index lang tayo. So si BI plus 1 at saka si BI isinulat ko using this equation. Pero dahil may mga I plus 2 siya, nagbaba ako ng index. In-adjust ko yung index. Binawasan ko lahat ng index by 1. Kaya makukuha ko itong equation na ito. Okay? Now, what's the nice thing about this equation is that this is an equation, etong right-hand side ay constant. Kasi yung mga H sub i's at mga A sub i's ay alam na natin from the problem. Okay? And then, yung left-hand side, okay, alam na natin yung mga H sub i's, so no problem about them. So they will only involve the C sub i's. Yun na lang yung problema natin. And remember, it's fine because we are solving for the C sub i's, and the C sub i's can be used in order to find the B sub i's and the D sub i's. So what we'll do is, this will be true, I going from 2 until n. All right? Remember, we have n minus 1 equations. So to toto, for starting from 2 to n, so pwede ko itong i-arrange into a system of equations para sa mga C sub i's. And what better way, or there's no better way to write a system but as a matrix, both for brevity and computational reasons. So isulat ko siya sa matrix, I'll get equation 4.11. Kung gusto nyong i-double check, pag minultiply ko itong row na to by this column, I will get what? I'll get H1 C1 plus 2 H1 plus H2 of C2 plus H2 C3 equals this guy. Okay, and this is the instance of equation 4.10 when I is equal to 2. When I is equal to 2, you'll get this guy. So talagang nire-arrange ko lang siya into an equation, into a matrix equation, yung system natin. Okay. So ito yung system natin para sa mga C sub i's, kasi ito yung gusto nating i-solve. Kaya lang ang problema, itong system na to ay n plus 1 by n plus 1. Okay? Ang problema ay kulang tayo ng dalawang equations, remember? So kulang tayo ng dalawang equations Saan sila manggagaling? Well, bakante yung top and bottom rows for both the left and right-hand side. So yung mga entries nila manggagaling dun sa additional conditions na i-impose natin. Kasi pag sinabi natin cubic splines, 5 lang yung requirements. Pero yung 5 requirements na yun, they do not completely determine or characterize the cubic splines. So kailangan natin magdagdag ng 2 pang equations. Alright? At yun yung 2 conditions na papasok sa top and bottom rows. Pero ang idea is, once we completely determine this system, magkakaroon lang tayo ng coefficient matrix X, unknown, vector of unknowns X, and equals vector of constants. Yan lang yung itsura ng equation natin. Tapos, we can ask our solvers to solve this linear system for us. So the solution to this, provided that A is invertible, ay equals A inverse B. So pag in-apply natin yung A inverse times B, makukuha natin yung C sub i's, makocompute natin from the C sub I si B sub I at saka si D sub I, and then we're done kasi alam na natin yung A sub i's. So the remaining problem here is what would be the top and the bottom row of this matrix equation. And we will talk about the common impositions on the top and the bottom row to completely determine our cubic spline next time. So magko-consider tayo ng specific cubic splines para mapunan natin yung top and bottom row. But let's have it done on Friday. Okay? So I'll end here. Any questions? Sorry, medyo messy at maraming pinagdaanan. Pero ano lang naman siya, algebraic lang naman yung mga nangyari. I skip most of the details kasi simple algebra lang naman yung ginawa niya. Ang maganda kasi ma-appreciate natin yung process. And that's what we want you to learn from Math 174. We just don't want you to apply out of the store or out of the box na algorithms. Kasi if you want to do that, then sana tinuro na lang namin kasi one-liner lang to kay MATLAB. Isang command lang to kay MATLAB. At saka may mga existing programs naman para i-define yung cubic splines. But in Math 174, we want you to dig deeper into the methods and understand how they work. So, paano sila nag-work, ano yung mga advantages at disadvantages nila, para pagpunta nyo ng SP o pagpunta nyo ng actual research, alam nyo kung ano yung appropriate method na gamitin. And who knows, maybe if you encounter a certain problem, you might devise your own method. So kukuha kayo ng method na natutunan nyo, tapos i-manipulate nyo siya ng konti para maging suitable na siya dun sa gusto nyong application area. So we don't just want you to apply algorithms, but to analyze and modify algorithms to your liking, right? Kasi kung gusto lang namin kayong mag-solve at mag-apply, kaya naman itong gawin ng accountants, kayang gawin ng computer scientists para mag-program and so on. But we want you to dig deeper kasi tayo yung inaasahan na mag-imbento ng mga methods. And that is the starting training that we want you to get from Math 174. Okay? So kaya wag na kayo magreklamo kung bakit diniderive pa natin. Yun yung point. Kasi otherwise, magiging parang programming class lang tayo. Kung ibibigay na namin yung algorithm, wala nang derivation, ito yung algorithm, i-program nyo. Okay? So what I suggest is you guys start trying to encode this matrix. Kung makapagawa na kayo ng program para mag-encode nitong matrix na to, given yung H sub i's at saka yung A sub i's, the better. Para kukunti na lang yung gagawin nyo for your lab exer 2, which is due on the 28th. So, yeah. Any questions? Okay, kung wala ng questions, sorry, I overtime na ako ng 1 minute. But thank you for getting up early and joining me today. So enjoy the rest of your day and let's see each other again on Friday. Bye, everyone.
Thank you po, sir.
Yeah, you're welcome.